because that's what we know. Or if you remember normal and tangential component, so we have a T and a N. And what is the tangential component? In this case, this is the tangential component. It's what we said dV dt times R. Actually, this is just dV dt, right? And the velocity here is actually, what's dV dt? The velocity here is actually omega times R, right? So here, this result becomes R doesn't change. So that means it just becomes d omega dt, which is alpha. That's from normal and tangential component. And the normal component, as we already know, is omega squared times R. So you have two ways to figure this out. Either you use simply angular motion, which may be more straightforward, or you use what we learned, what we talk about in tangential and normal component. And this will also give you the same result. It's still alpha times Rg. For this problem, Rg is 1.5 meters. Therefore, Ag is just 12.5 times 1.5, and that is what, 18.75 meters per square second. That's how we found the linear acceleration at the center of gravity. All right. Any questions on this? Nope. It should be very straightforward, right? Just the only thing you want to pay attention to is this, which is the concept, important concept here. For the moment equilibrium, you have to remember that on the right-hand side, if you choose to use the mass moment of inertia at the center of gravity, on the right-hand side of the moment equilibrium, you always have three terms. But if you choose to use the mass moment of inertia at the center of rotation, it will reduce to just one term. And the fundamental reason is because of parallel axis theory. This is the most important point in this example. Okay. For some reason, I feel this whiteboard is falling apart. The vibration, the level of vibration increases significantly over 1 week. I think the joints are losing its rigidity over time. All right. Okay. Next topic is kinetic equation. I'm sorry, kinetic energy, not kinetic equation. Kinetic energy. And this is on my notes, page 49. What is kinetic energy? And in fact, I talked about this already, right? I talked about this before in linear or rectilinear motion. Kinetic energy has only one term, which is 1/2 of mass times the linear velocity squared. We only have that. And if it's angular motion, kinetic energy equals to 1/2 of mass moment of inertia at the center of gravity, of course, assuming that the center of gravity is the center of rotation, times omega, which is the angular velocity squared. That's the form in angular motion. Now, of course, you will know that when the center of gravity is not the center of rotation, this IG will have to be replaced with IA. So in planar kinetic equation of motion, the way we consider kinetic energy is to consider both. Because in general, an object can actually move whatever it wants, right? Remember what I summarized last time. I said that there are two different kinds of motion in the planar or general motions. The first one is what we call unconstrained. What is unconstrained motion? Unconstrained motion is very simple. That means the center of gravity is the center of rotation. So you can say that G is equals to center of rotation. That means what? That means unconstrained. What is unconstrained? Like the example I did before, remember? This is unconstrained. Because while this eraser is spinning and also moving in air, there's no constraint. In that case, the center of gravity is the center of rotation. That's unconstrained motion. And I mean, you can just use all of this. When it happens, you will use this. Kinetic energy equals to 1/2 of mass times the velocity at the location of consideration. Whatever you want to consider it, find out the velocity at the point. Plus 1/2 of mass moment of inertia at the center of gravity times angular velocity squared. So this is the kinetic energy in unconstrained motion. When it's constrained motion. So what is constrained motion? Remember, I talk about this, the motion of a pendulum. Right? Suppose I have a pendulum like this, something like that. Right? And I want to release the pendulum from this position. And you know gravity is going to draw, can pull this thing going downward. So the motion is going to go like this, correct? Because of gravity. Each one of them subjected to gravitational force. G1, there's G2. Right? We know that. Now in this case, the center of gravity is somewhere between G1 and G2, correct? It's somewhere here. It must be between these two, so maybe it's somewhere here. This is the real center of gravity. But where's the center of rotation? It's at the support. So the center of rotation is not the center of gravity. This is what we call constrained motion. Of course, that means G is not center of rotation. What does that mean? It means this. When you calculate kinetic energy, mass will never change. Mass is always mass. Your linear velocity here will have to consider other terms. As you know that the conversion from the linear velocity yields relative motion. That means here, because before, if it's unconstrained motion, the location of whatever point you want to consider is fine. But in this case, the center of gravity is not the center of rotation. So here, usually what we do is use the velocity at the center of gravity plus, of course, or minus omega times r. And this whole thing squared. So what does this come from? This is coming from relative motion. So the source of this one is coming from relative motion. And relative motion, remember what we did this. VB equals VA plus VBA, right? So this VBA in angular motion is just omega times r. Of course, it should be omega cross r. in vector forms. But in planar motion, they're always perpendicular. That's why we say planar motion. In planar motion, they're always on the same plane. So omega is always perpendicular to r, because the direction of omega is our plane. So that r is on the plane, omega is our plane. These two are always perpendicular. For this, for the angular term, this becomes 1/2 of I. It's not IG. It has to be the center of rotation. So suppose we use IA, for instance, just like the example we used before, times omega squared. So just be careful that this is different from this. All right. Okay. Now, once we understand the formulation, we can continue with the example. 26. So what is this example about? Okay, this is a pendulum problem. So you have a pendulum, looks like this. Has a disc part like that. And the diameter of the disc is 0.8 meters. And the length of this bar is 2 meters. The disc has a mass of 10 kilograms. And the bar has a mass of 3 kilograms. So what are we finding?